This is my presentation on azithromycin. So azithromycin is a medication that's used to prevent and treat HIV and AIDS. You can see the structure in the picture on the left. It is actually the first drug that was approved by the FDA for treatment of HIV, so it's a pretty big step for that. It's also an important part of antiretroviral therapy regimens. However, it does have some downsides to it. Some common side effects that have been seen are anemia, neutropenia, gastrointestinal issues, and mitochondrial toxicity when used over a long period of time. It belongs to a class of drugs called nucleoside reverse transcriptase inhibitors, and it is a synthetic analog of thymidine, which means it is a building block of DNA. It has an azido group replacing the hydroxyl group on the 3' carbon of the deoxyribose sugar in thymidine, and this is what allows it to interfere with the replication of the viral DNA. Like I was explaining before, here's the pictures of the structures on the left. AZT has to be converted into its active form to be used as the treatment for HIV. So it enters the body's cell through passive diffusion, and then once inside the cell, it undergoes phosphorylation to become the active form. And this is catalyzed by 3 cellular kinases. Those 3 are thymidine kinase, which converts the AZT to AZT monophosphate. Thymidylate kinase converts that to AZT diphosphate. And nucleoside diphosphate kinase converts that to AZT triphosphate, which is the actual active form of the drug. The mechanism can be seen on the right here in that picture. HIV relies on the enzyme reverse transcriptase to convert its RNA genome into DNA, and the active form of the drug resembles the natural nucleoside thymidine triphosphate, which is used by reverse transcriptase to synthesize viral DNA. So because of this, it can be incorporated into the growing DNA chain by reverse transcriptase and act as a chain terminator, which is necessary for the addition of the next nucleotide. By doing so, it can halt the DNA synthesis, preventing the virus from replicating its genome and making more of it. It does have specificity. It has a higher affinity for HIV reverse transcriptase compared to cellular DNA polymerases, which are responsible for the replication of host DNA. And while it can potentially inhibit human DNA polymerases, it primarily targets the HIV reverse transcriptase due to the higher incorporation rate into the viral DNA. There are 3 things involved in the cellular machinery. Kinases, the 3 that I listed earlier that are used for the phosphorylation. There are reverse transcriptase, which is the viral enzyme that is the primary target of the drug since its function is to synthesize DNA from an RNA template. And DNA polymerases, because while the drug primarily targets reverse transcriptase, cellular DNA polymerases could also be affected still. In conclusion, AZT is converted into its active triphosphate form through a series of phosphorylation steps by cellular kinases. It's then incorporated into the viral DNA by HIV reverse transcriptase, causing chain termination and halting the replication of the virus. It has specificity for HIV's reverse transcriptase over human DNA polymerases, which allows it for targeted inhibition of the virus with less impact on the host cell DNA synthesis. Overall, AZT plays a crucial role in the treatment of HIV and AIDS, and its development marked the beginning of effective medical intervention against HIV, which has paved the way for the development of other antiretroviral medications and other combination therapies that can be used to help people suffering with HIV and AIDS. So it's very important.